Hello. In our interpretation of reality, observable macroscopic physical phenomena are the result of a large number of elementary processes in a microphysical world where it is impossible to track every element, for example, every molecule in a gas. So, to compensate for man's inability to track individual molecules in large aggregates, we carry out a probabilistic study based on statistical data. In quantum physics, because of the uncertainty principle, indeterminacy is inherent in the nature of things and can never be surpassed by improved technique or increased skill. We cannot know the state of a subatomic system, only its probability of being in a given state. These statistical results enable us to predict physical phenomena such as the behavior of a gas or radiation. But even in this case, our statistical applications are based on assumptions, notably that all molecules or particles of the same type are similar. In quantum mechanics, indistinguishability being posited as a principle. Furthermore, they are assumed not to have any of the characteristics of living organisms, and in the case of a molecule, that it has the same probability of being in such and such a place. However, despite these assumptions, at the observable macroscopic level, we obtain sufficiently satisfactory results. For philosopher of science Deborah Mayo, it is difficult even to tell what is true about the different methods of statistics. So perhaps it would have been prudent to stick to these successes and not venture too far in applying these methods outside the microphysical world. Indeed, such applications raise many questions concerning not only misuse, whether deliberate or the result of a misunderstanding of the concepts, but also the very realism of the concepts themselves. The problem is that, starting with a small sample, the aim is to reach reasonable conclusions about the population as a whole. The closer we get to the human sphere, with all its diversity, the more the validity of such an approach raises questions. The sample must reflect the diversity of the traits that have an impact on the study. But can we know all the traits concerned and take them all into account? They may be far too numerous, difficult to identify, and interconnected. Take the case of a poll on voting intentions. We can assume that age and social category have an influence, but so do the distance between the place of residence and the nearest metropolis, as well as education and so on. So from the outset, a subjective choice has to be made about which traits are considered to have a sufficient impact. Then, for the sample to be random, namely to reflect the population as a whole, we need to know the distribution of the traits selected in the general population, and the sample needs to be sufficiently large. For measurable traits, we could theoretically force each person to reveal the data, and a simple calculation would suffice. But these are methods of a totalitarian state. The estimate of this distribution is far from objective. The pollster then divides the population into non-overlapping groups according to the selected traits. This method is called stratified random sampling. But there could be more than one reasonable way of delimiting the strata. If an interviewer is asked to interview a certain number of people in each stratum, then the subjectivity of the interviewers may play a role. In the same category, they may, for example, prefer someone whose appearance or house they find more attractive. Other unquantifiable human elements are likely to affect the results of a survey. The people surveyed may not tell the truth, a reflex that is often unconscious, a reluctance to display a politically incorrect opinion in front of others. Others may refuse to take part in a survey and not return the questionnaire. This is more common among the more active strata of society, further reducing the validity of the survey. Pollsters rarely mention the percentage of responses received in each stratum, information they probably do not themselves know. If the respondents are not sufficiently familiar with the subject in question, the results will only reflect a point of view based on ignorance or prejudice, leaving open the possibility of a manipulation of opinion. The wording of questions and multiple choice questionnaires with a necessarily limited number of pre-established answers can also serve as means of manipulation. Added to all this is the cost of a poll. Of course, in order to keep costs low, we may prefer not to apply the best methodologies. For example, when polls are published non-stop in the months and weeks leading up to an election. Polls are therefore often unrealistic and can be used to shape public opinion. The election results justifying the polls a posteriori, making them appear impartial. We can also select samples that serve our purpose, but are unrealistic, especially as we can find them by trying and trying again or selectively reporting, as Mayo writes. Namely, physician and author Ben Goldacre explains, when the results are unflattering, we often fail to publish them. According to him, in the pharmaceutical industry, it's a case of whole studies going missing by the hands of hundreds and thousands of individuals spread around the world in both the public and private sector. Patients are often chosen so that they have a better chance of improving with the treatment, and the control group given a placebo are selected in such a way that they show signs of poor health. Moreover, even in the best of cases, as we have seen, we cannot really know whether the control group is a true reflection of the general population in terms of the factors affecting health. It should be noted that there is little point in conducting a double-blind or other statistical study if treatment is truly effective and without harmful effects. So the use of such studies is often the consequence of a profit-oriented society. Which brings us to the question of the reliability of results. There is inevitably a margin of error when extrapolating from limited data to an entire population. As we saw in the previous video, it's unrealistic to assume that traits are normally distributed. It would be more correct to talk about an ideal distribution rather than a normal one. The first step is to estimate whether the sample is random, namely represents the general population, or on the contrary is not representative, in which case it is said to be significant, namely a phenomenon that requires explanation. For example, the decision to list an adverse drug reaction depends on the extent of the reaction in a sample of patients who have taken the drug, compared with the extent of the reaction in the general population of patients with the same disease who have not taken the drug. More precisely, we estimate the p-value. In other words, the probability p of the data observed and of less likely data, assuming that a hypothesis called the null hypothesis is true. We therefore need to know the distribution of the data and their probability according to this null hypothesis. For example, suppose you wish to know whether a coin is biased or not. We take for our null hypothesis H0 the hypothesis that it has equal probability that it lands on heads or tails, namely probability half, which would be the case were it unbiased. Suppose you toss it 3 times and it lands on tails each time. The probability is 0.5 to the power 3 equal to 0.125. And this is the p-value since it is the least likely data if you toss it thrice. No, according to the convention following the suggestion of one of the founders of modern statistics, Ronald Fisher, which considers the data significant if p is smaller or equal to 0.05. So if you toss it 5 times and you get tails 5 times, then the p-value being 0.5 to the power 5, which is equal to 0.03125, you would then be able to conclude that the coin is biased. In short, a result would be significant if p equals to 0.049 and non-significant, namely random, if p equals to 0.051. This is absurd, as philosopher Christine Schrader-Frechette points out. In certain contexts, we take p smaller or equal to 0.01. These choices are subjective. In the context of a study, any conclusion about the effectiveness of a drug or its adverse effects depends on the threshold chosen for p. Moreover, just because an experiment has a result with a low probability does not mean that if we repeat it, the probability of the result will always remain low. Also, the p-value does not answer the question to which we would like an answer. Given the data, what is the probability that the null hypothesis H0 is true, namely that the data is distributed according to H0? It is a common logical error to conclude that a low probability p-value implies that H0 is false. Nor does the calculation of p allow us to conclude anything about the truth of an alternative hypothesis to H0 concerning the distribution. Legally, the use of statistics can have serious consequences. When there is a lawsuit against an industry for damage caused by pollution or a drug, judges very often ask for a study of statistical significance before establishing causality. Just because p is greater than 0.05 does not mean there is no causality. Nor does the fact that there is a degree of causality if there is some correlation. In many fields, the methods for estimating correlation are dubious. This is often the case in neuroscience. fMRI, functional magnetic resonance imaging, shows which areas of the brain are more oxygenated and therefore more active during the emotion or activity in question. A volume of images is made up of vaguely cube-shaped regions called voxels, volumetric pixels. Each image contains between 40,000 and 500,000 voxels, each voxel being between 1 millimeter cube and 125, that is 5 times 5 times 5 millimeter cube in size. Images are taken every 2 to 3 seconds, giving a time series. In this mass of data, it is certain that we will find a correlation between cerebral activity at certain points and behavioral measurements. So it's hardly surprising that studies that have analyzed the correlations given in the literature have found them to be exaggerated. What's more, only objects are measurable. So this reduces a human being to an object. On top of that, you have to be very careful when you talk about the average without specifying what it really is. Is it an arithmetic mean or the median? For example, let's consider the estimation of average income. Suppose that in a company, the CEO earns 45,000 euros a month, the vice chairman 15,000 euros a month, 2 other members of the administrative board 10,000 a month, 3 specialist technicians 5,000 a month, 5 technicians 3,700 a month, and 12 other employees 2,000 a month. That's 24 people. So the median, being the point in the middle, is the salary that is midway between the 12th highest salary and the 12th lowest salary, namely 2,850. But the CEO may want the arithmetic mean, which is around 5,729 euros, a significant difference. This example also shows the approximations made. It is in fact 5,729.1.66666 and so on. In a large calculation, approximations can lead to larger errors. In conclusion, a statistical study can only be vaguely indicative. Any conclusion about a phenomenon must be based on a reasoned study based on observation that can be reproduced at will, in other words, a scientific study. Such a study already contains many weaknesses, and we cannot know whether it reflects reality. Observation cannot be carried out outside a theoretical framework. We therefore tend to see things according to our preconceptions, and any generalization is problematic. But such a study is essential. It is our best and only way of ensuring that we come to somewhat satisfactory conclusions. That said, when we know scientifically that a phenomenon has biological effects, except in extreme cases, not everyone will die or fall ill. We can only assess the risk statistically and therefore uncertainly and subjectively. In the case of technology, it is then more a matter of society deciding what kind of technology, particularly medical technology, it wants. Is profit its aim? Statistics are certainly necessary when that's the aim. And then we're faced with a battle of figures, depending on the point of view, as we will see in the next video. The belief in the objectivity of figures serves to conceal the fact that the policies implemented and the choices made by society are a matter of opinion and not of statistical expertise, since the figures and models given are themselves a matter of opinion. Above all, statistics remain what they were originally, a science of the state. The more totalitarian a state is, the more it needs data, even if it has no real meaning. Thank you.